is lesson 4 on transformations. So in this lesson, we're going to be doing transformations of power functions, and we learned what power functions were earlier in the unit. So you should remember from previous courses what the parameters a, k, d, and c do to transform any function. We're just going to apply those parameters to power functions, like you see here. Before I take you through the investigation where we do transformations to this power function x to the 4, let me just open up Desmos and give you a quick visualization of what those parameters a, k, d, and c do to transform a function. So here in Desmos, I have this x cubed function. And to that x cubed function, right, we can see this is an x cubed function. I'm applying the transformation parameters a, k, d, and c to that x cubed function. Let's just quickly play around with those parameters to get a refresher on how that affects the shape of the graph. The first thing I want you to look at is the parameter a. Now the a parameter, which is the factor in front of the power function, can do a couple different things. If I make a negative, it's going to do a vertical reflection. Hopefully you could see that vertical reflection happening as I made it negative. But it can also do a vertical stretch or compression. So watch as I manipulate this a value. It could do a vertical stretch if the a value is bigger than 1. So imagine someone grabbing the ends of this and stretching it vertically. It would also do a vertical stretch if the a value is less than -1. So let me set it to -1. So now it's going from quadrant 2 to 4 instead of 3 to 1 because it's been vertically reflected. And now let me make this a value less than -1 and notice it's also getting vertically stretched. If I let a equal something between -1 and 1, it's actually going to do a vertical compression. Picture someone squishing it from above and below and you'll see what's happening. So the parameter a actually does a vertical stretch or compression by a factor of the absolute value of a. If a is negative, that just causes the vertical reflection. Now let's look at the k parameter and what that's going to do to transform a function. And that's actually going to do horizontal stretches or compressions. And it could also do a horizontal reflection if k was negative. Watch as I make k negative. Picture it flipping horizontally across that y-axis. Now for an x cubed function, you might say, okay, well the horizontal and vertical reflections actually do the same thing. And you're right, for an odd degree power function, that'll be the case. But let's watch what happens as I make k bigger than 1. It's actually going to do a horizontal compression by a factor of 1 over the absolute value of k. And if I make k less than -1, let me set it to -1. If I make it less than -1, once again, horizontal compression by a factor of 1 over the absolute value of k. If k is something between -1 and 1, it does a horizontal stretch by a factor of 1 over the absolute value of k. Picture someone grabbing the sides of this and stretching it out. The d value, if d is something bigger than 0, like let's say 3, it's going to shift right 3. If d is something less than 0, it's going to shift left by the absolute value of that amount. So if I make d -3, notice it shift left 3. Now, if this d value of -3 was in this equation, it would be x minus -3. So it would look like x plus 3, but you would have to know that based on this format of the transformed equation, the d value would actually be -3. And a c value shifts it up and down. Okay, let's complete part 1 of this lesson, where we're going to kind of go through an investigation like I just showed you in Desmos, but we'll actually record our answers. So in this investigation, we'll be looking at transformations of the power function y equals x to the 4. And we'll complete a bunch of tables of different transformations. So we're going to go through the parameters a, k, d, and c one at a time to show how they transform the function y equals x to the 4. It's important to know that the parameters k and d are going to affect the base of the power. They're the horizontal transformations. So the base of the power would become k times x minus d. And the exponent of 4 will be on it because this is a transformed x to the 4 function. And then to that power, the vertical transformations happen. We multiply it by a, and we add c. So notice the location of the parameters a, k, d, and c, and let's go through what they do one at a time. So let's start by looking at the effects of the parameter c on the x to the 4 power function. So if we add c to the x to the 4 power function, what happens? So in Desmos, I've changed it so I now have the x to the 4 as the parent function, and we're going to apply transformations to it. Let's manipulate c first. So in this one, the c value is 1. So if I make the c value 1, let's look at what happens. Notice the transformed function, the purple one, is 1 higher than the parent function x to the 4th, so it's been shifted up 1. And just do a quick sketch of the graph that is 1 higher than the parent function. So you're given this red graph, just sketch the purple one, should look exactly the same, just 1 higher. And then let's make the c value -2 and see what happens. So if I change the c value to -2, notice the transformed function is now 2 below the parent function. Exact same shape, just been shifted down 2 units. You can sketch that graph as well. Let's look at the effects of the d value. Remember, the general format is x minus d, so in this equation, x minus 2 to the power of 4, the d value is actually 2. Which, let's look at what happens if the d value is 2. So let's set the d parameter to 2, and notice that it shifts it right 2 units. So it shifts it right 2 units. You can sketch that graph. For this transformed function, it looks like it's an x plus 3 to the power of 4. In order for it to look like this, the d value must have been -3. Because if I plug -3 into this equation up here, it would be x minus -3, which simplifies to x plus 3. So what does a d value of -3 do? Let's make the d value -3. Notice compared to the parent function, it has been shifted left 3. So you can sketch that graph as well. Now let's look at the a value. So the a value is the factor that's in front of the power. If I make the a value 2, let's see how that affects the graph of the parent function. Notice it looks like it's getting thinner, and we call that it's being vertically stretched by a factor of 2. All of the y values are now twice as high. Just look at when x is 1. When x is 1, the parent function is at 1, but the transformed function will be twice as high. It'll be at 2. So we say vertically stretched by a factor of 2, and draw the corresponding graph that's been vertically stretched. For each x value, the y values are twice as high. If I make a 1/2, well, that would mean the y values are going to be half as high, so that's a vertical compression by a factor of 1/2. So let me show you on here. Let's set a to 1/2, and there we go. Notice that it's been vertically compressed. It's like someone from the top has squished it down. When x is 1, the parent function is at 1, but the transformed function is half as high. It's at 0.5. Let's make a negative. So when a is -2, notice it has also been flipped upside down. The original function, when x is 1, the y value is at 1, but the transformed function when x is 1, it's been flipped upside down and doubled. So it's down here at -2. So we'd say two things for this a value of -2. There's been a vertical reflection and a vertical stretch by a factor of the absolute value of a. So a vertical stretch by a factor of 2 and a vertical reflection. Let's look at k. K is part of the base of the power. That's how we can distinguish it from a, which was not part of the base of the power. So in this case, the k value is 2. It's being applied to the x before the power of 4. Let's look at what that does. If I increase k up to a value of 2, what's happening is a horizontal compression by a factor of 1 over the absolute value of k. At any given y value of the function, the x value is now half as far from the x-axis. Here, at a y value of 1, x is 1, but if I go over to here, the transformed function when y is 1, the x value is now half of that. It's 0.5. So we'd say a horizontal compression by a factor of 1 over the absolute value of k. And there's what the graph looks like, a horizontal compression. How about k if k is a third? Let's set k to a third. Let me get it exactly a third. Let me write the fraction. There we go. Notice it's been horizontally stretched. By what factor? Well, when the y value was 1 on the parent function, we know x was 1. When the y value is 1 on the transformed function, what's the x value? It's over here. It's been tripled. It's 3. So it's actually been a horizontal stretch by a factor of 3 when the k value is a third. So a horizontal stretch by a factor of 1 over the absolute value of k, and 1 over a third, that means it's reciprocal, so 3. Here the k value is -2. For an even degree power function, that's actually going to do the exact same thing as a k value of +2 did, because when k is negative, it does a horizontal reflection, but even degree power functions are already symmetrical about the y-axis, so the horizontal reflection, you're not going to notice anything. Look at what I mean. If k is 1 or -1, you don't see any change at all. Doesn't matter. If it's an even degree power function. Odd, different story. So let's set k to -2. It's been horizontally compressed by a factor of 1 over the absolute value of k, so 1 over 2. So the x values are half as far from the y-axis now. And there technically was a horizontal reflection, but it doesn't cause a change in the graph. And notice when I'm describing the horizontal compression, it's always by a factor of the absolute value of 1 over k. The negative is just what causes the reflection. Okay, so on this slide, we have a summary of all the rules about what each parameter does and when it does it. So if c is positive, it shifts the graph up. C is negative, it shifts the graph down. If d is positive, it shifts right. If d is negative, it shifts it left. But keep in mind the d value will always appear as the opposite sign of what it is because of the fact that the general template for a transformed function is x minus d. A does a vertical stretch by a factor of the absolute value of a if a is bigger than 1 or less than -1. Does a vertical compression by a factor of the absolute value of a if a is between -1 and 1. And if a is negative, we also say there's a vertical reflection. K is like the opposite of a. If k is bigger than 1 or less than -1, there's a horizontal compression by a factor of 1 over the absolute value of k. If k is between -1 and 1, it's a horizontal stretch by a factor of 1 over the absolute value of k. And if k is negative, there's a horizontal reflection. And I mentioned this already, but a and c cause vertical transformations and k and d cause horizontal transformations. Which means, algebraically, when we're coming up with transformed points, a and c are going to affect the y-coordinates, k and d are going to affect the x-coordinates. Okay, let's complete part 2, where we're going to describe transformations from an equation. So example 1 says, describe the transformations that must be applied to the graph of each power function, f at x, to obtain the transformed function, g at x. Then write the corresponding equation of the transformed function. Then state the domain and range of the transformed function. So in this question, part A, the parent function, f at x, is equal to the power function x to the 4. And what's happening to that parent function f at x is that an a, k, and d parameter are transforming it. Let's actually start by writing the equation of the transformed function. Let's make sure we apply the horizontal transformations, k and d, to the base of the power. Right, it's f at this value. So what we have to do is, in the f at x function, replace the x with that. So the transformed function is now a 1/3 times x minus 5 to the power of 4 instead of just an x to the 4. And don't forget the a value goes out front of the power, so a 2 goes there. So that's the equation of the transformed function, knowing that the parent function is an x to the 4 function. Now let's describe what those parameters a, k, and d are going to do to transform the function. Well, the a value we can see is 2. That's an a value bigger than 1, so it's going to do a vertical stretch by a factor of 2. So how we would apply that algebraically is we would double the y values. So in brackets, you'll just see the algebraic transformation for if we were to actually transform a table of values, which we'll do in the next example. The k value is 1/3. So this k value of 1/3, that's between -1 and 1, so that does a horizontal stretch by a factor of 1 over the absolute value of k, so by a factor of 3. So what that does is it triples all the x values. And the d value is +5. And what that does is it's going to shift the function right 5, and we could accomplish that by adding 5 to all the x coordinates. Part B, the parent function is now x to the 5, and our transformed g at x is a transformed version of f at x. It has an a, k, d, and c parameter transforming at this time. So once again, why don't we start by writing the transformed function's equation. So the transformed function g at x is the f at x function, but it's f at this. So we replace the x in the parent function with that. And then we'll apply the a and the c parameters outside of the power. So the g at x function would equal this negative 2 times x minus 3 being raised to the power of 4, with the a value of 1/4 and the c value of 4 being multiplied outside and added to that power. So now let's talk about what the a, k, d, and c parameters do. So the a value of 1/4, that's going to be a vertical compression by a factor of 1/4 because it's an a value between -1 and 1. So what happens is the y values need to be multiplied by 1/4 or divided by 4. The k value of -2, since it's less than -1, is going to do a horizontal compression by a factor of 1 over the absolute value of k, so by a factor of 1/2. And then the negative is what does a horizontal reflection. So what happens is we have to multiply the x's by -1/2, or divide them by -2, same thing. The d value is 3, that's going to shift it right 3, so we'd add 3 to the x's, and the c value is 4, that means shift it up 4, which means add 4 to the y's. Okay, the next two examples are actually going to be graphing questions. Example 2, the graph of x cubed is transformed to obtain this transformed function g at x, which has an a, k, d, and c parameter doing the transformation. So before I actually graph this transformed function, let's state the transformations in words again. So the a value is 3, which does a vertical stretch by a factor of 3. The k value is -2, which does a horizontal compression by a factor of 1 over the absolute value of k, so 1/2. And the fact that it's negative means a horizontal reflection. D is -1, which shifts it left 1. And c is 5, which shifts it up 5. And notice in brackets, I have all the algebraic transformations which accomplish what I've written in words, which is what we're going to have to do to a table of values at points to come up with points for a transformed function. So when we do these questions, we're always going to fill out two tables. We're going to fill out a table of values for the parent function x cubed, and for that parent function, we're always going to choose x values -2, -1, 0, 1, 2. Those x values will give us a good shape of the parent function, which will then result in a good shape for the transformed function. So if I plug these x values into this x cubed equation of the parent function, -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. These are points for the parent function. Now let me do the table of transformed points. So this table is going to be for our g at x transformed function. Okay, so let's figure out what's going to happen transformation-wise to the x values and the y values. Now, the general template of what we do transformation-wise, I mean, we already wrote them over here that we're going to do, so we just have to apply those transformations to our table of points for the parent function, and then we get a table of points for the transformed function. But the general template that you can follow would be to get the transformed values for x, we take these x values and do each of those x values divided by k, because the effect of k is always done by its reciprocal, so we do x divided by k, and then we have to do the horizontal shift by adding the d value. So you can always do x over k plus d. So in this case, that would mean to each of the x values, we divide them by -2, and then add -1. So I could just write -1. And to the y values, what we always do is we multiply the y values by a to do the vertical stretch or compression, and then we add the c value to shift it up or down. So ay plus c is what we always do there. So in this case, it would be 3y plus 5. So we need to do those sets of transformations to these x and y values, and then we get points that are on the transformed function. So let's take all of our x values and plug them into here for x, and then we will get the x values for our transformed function. So let's start with -2. If we plug it in for x into there, we would get -2 over -2, which is 1, minus 1 is 0. Now let's take -1, plug it in for x, and we would get 1/2 minus 1, that's -1/2. Plug 0 in, we would get -1, plug 1 in, we get -1.5, plug 2 in, we would get -2. So those are the x values for the transformed function. Now to get the y values, I guess we have a couple of options. What I'm going to do is do these transformations to these y values. But I suppose what I could do is I could take these x values and plug them into x into the transformed equation. We should get the same answer either way, and it would be a good way to check your work. But let me transform these y values. That's the way I'm going to do it. So I'm going to take negative 8 and plug it in for this y value. So that'd be negative 24 plus 5, that's negative 19. Take negative 1, plug it in for this y value. Negative 3 plus 5 is 2. Plug 0 in, get 5. Plug 1 in, get 8. Plus 8 in, I get 29. So here's a table of points for the transformed function. Let's graph the parent function and the transformed function. So parent function, 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. Just careful with the scale here. So there's my f at x function. And now we'll do the transformed function. Okay, there's a rough sketch of the graph, and we can compare that to what Desmos would give us. It's pretty accurate. Now you should always do a check after. What you wrote in words about the transformations should match what it looks like on your graph as well. In words, we said it was going to be vertically stretched and horizontally compressed, so it should be a lot thinner, which it is. And we said it was going to move left and up, which it did. Good. Let's do one more practice of the same type of question. This time, the graph of x to the 4 is being transformed, and here's the transformed version of it. But remember, the transformed version of a function should always have the k value factored out from x plus d in the base of the power. And this one doesn't. This 1/3 is not a factor of x plus 2. So what we need to do is factor out that 1/3 to get it into this format for the base of the power. So if I start by doing that, divide the third out from the x and the 2, that leaves me with x and 6. A third x divided by a third is x, and 2 divided by a third is 6. So now that it's in the proper format, you should be able to tell what your a, k, d, and c values are. The a value is negative 1, which is going to cause a vertical reflection. No stretch or compression, because multiplying things by 1 doesn't make them bigger or smaller. The negative just does the vertical reflection. The k value is a third, so that's a horizontal stretch by a factor of 1 over a third, which is 3. The d value is negative 6, which means move left 6, and the c value is negative 1, which means move down 1. So let's do those transformations to the x to the 4 function. So we need some key points for that parent function. So choose the same x values, negative 2, negative 1, 0, 1, 2. Plug them into this function to get the y values. Negative 2 to the 4 is 16. Negative 1 to the 4 is 1, and so on. And now we're going to transform those points to come up with the equation for our transformed function. And it was g at x equals negative a third x plus 6 to the power of 4 minus 1. So if we follow the general template we're supposed to follow for transformations, and if we just follow what we wrote in words, we do x over k plus d here, and ay plus c here. So when I do x over k, x over a third, well, that's just 3x. And plus the d value of negative 6, so that would make this minus 6. And ay plus c, well, a is negative 1, and c is also negative 1, so it's negative y minus 1. This will perform the correct transformations to these points. So take each of the x values, plug them into 3x minus 6. Take each of the y values, plug them into negative y minus 1. And let's see what we get. 3 times negative 2 is negative 6, minus 6 is negative 12. Plug in negative 1, we get negative 9. Plug in 0, we get negative 6. And so on. Now the y values. Plug in 16. Plug in 1. Plug in 0. Plug in 1 again, plug in 16 again. There's the table of points for our transformed function. Let's graph them both. There's the parent function, And now let me do the transform function. And there's the transform function. Make sure you have both functions labeled, and let's compare it to Desmos. Looks like we have a good representation of the transform function. Last part of this lesson, we're going to go backwards. I've given you the graph of a transform function, and we're going to write its equation. Example 4 says transformations are applied to each power function to obtain the resulting graph. Determine an equation for the transform function, then state the domain and range of the transform function. For this one, the red one's the parent function x to the 4. The blue one has been transformed. It looks like it's the exact same shape, it's just been shifted. To figure out the shift, let's compare the vertices. This vertice is at 0, 0. This vertice is at -3, -5. It looks like. We'll estimate that that's what it is. So in order to get the vertice to do that shift, we'd have to go left 3, down 5. Left 3, down 5. Well, to move left 3, the d value would have to be -3. And to move down 5, the c value would have to be -5. So our transformed function, I'll call it g at x, you can call it whatever you want, equals the x to the 4 function with those two parameters applied. So the d value is going to be applied to the base of the power, so it would be x plus 3 to the power of 4, and the c value is added after, so plus -5. So there's the transformed function. It also asks us to write domain and range. Domain, well, for power functions, the domain, there are never any restrictions. It's just from -infinity to infinity. The range, however, for this one, notice it never goes below a y value of -5, so we'd say from -5 to infinity. Part B. So the red one is the parent function x cubed, the blue one is the transformed function. If I look at this point right here, where is that moved to? It's been moved right 5. So to go right 5, the d value would have to be 5. But there's also been a reflection that's happened. And it could be a vertical or a horizontal. They would actually do the same thing for this. So you can pick either one that you want. Let me just prove to you that they do the same thing in Desmos. Okay, so there's x cubed. It wouldn't matter whether I made a -1 or k -1. They would do the same thing. So we can choose whichever one we want. I will choose the a value to be -1 in this case. So my transformed function, g at x, would equal negative. The a value has to go outside the base of the power. And the base of the power would be x minus 5. Don't forget to cube it because the parent function is x cubed. So there's my transformed function. It says domain and range. For odd degree power functions, there's no restrictions on either. So for both of these, we would just say -infinity to infinity. Okay, that's it for that lesson.